organization day anyway. Although, okay, why don't I pass some of these around? These are, I still do the old-fashioned thing because I never have trusted the registrar for the last 37 years. These are sign-up sheets, just so I know your email and department and your name. It has nothing to do with signing up for the course. You have to do that through the registrar. But it just helps me know early on because the registrar doesn't give me a list until much later in the term. Although it's getting better. I used to have to wait till 5th or 6th week of the term. I think I can get them within a lot quicker now. So you ready, Nicholas? Can you turn it on? So my name's Tom Eagar, and some of you have taken a version of this before. I teach 3 courses during the year, 3370, 3371, and 3372. They're all something about structural materials. And this semester I'll be lecturing, Dr. Belmar will be lecturing, and Ms. Balmforth will be lecturing. Mike is a certified welding engineer, certified welding inspector, and my module, which Mike will be doing with me jointly, is welding metallurgy. And Simone is going to be talking about uses of structural materials, and he'll talk a little bit about that, but it has to do with quality control and capacity of joints, or not joints, but of materials and whatnot. Today is sort of an introduction. The course is actually taught in a series of modules, and you have to take about 36 hours of lectures. And this is a sheet from right off my website. If you go to the MIT website and put in my name, you'll find something called Eagar Group, and on that you'll see this list of 12-unit modules, by and large, that I have taught in previous years. And now the website actually lists the year. So in last summer, I taught fusion welding. During the summer, I teach to the Course 2N students, which are Navy students, Navy officers who are about around 30 years old, plus or minus a couple of years, and they come back to get a couple of master's degree at MIT before they go off and design ships for the Navy and things like that. So they have to have certain things according to the Naval Sea Systems Command for their curriculum at MIT, one of which is welding metallurgy, which was covered years ago by Professor Masabuchi. When he retired, I started covering it, and so you might find 1 or 2 lectures on welding metallurgy in this 12 units of fusion welding, but you probably won't. It might be in some of these others. But this semester, Mike and I decided we would try to put together a real fusion welding course. But it is the metallurgy of welding. Okay, great, thanks. It's the metallurgy of welding, so in a sense, you can think of it as it's a crash course in physical metallurgy of different materials. And what Mike and I will be doing in the welding metallurgy this semester, we'll do a number of lectures on on steels. Then we'll do high alloys, which is stainless steels and nickel-based alloys. We'll do aluminum alloys. We'll do titanium alloys. We'll do what else are we going to do? Anyway, we can do any alloy you want. We can do iridium if you want. There is actually an application for welding of iridium about once every 25 years. They weld up little iridium spheres around plutonium, and when they have some space, NASA has a space shot that goes into deep space, like passing by Uranus or Neptune or Pluto. There's not enough sun light energy to power the spacecraft for 40 years, so they put a piece of plutonium in there which generates heat, and they have thermoelectric generators, which are very reliable reliable electrical sources, and they These things, the Voyager spacecraft that's been going for 30 or 40 years, is powered by a piece of plutonium surrounded in iridium, just in case it blows up when it's going up into orbit. Rather than spreading plutonium all over the Atlantic Ocean, they just end up with one little iridium sphere, and they can go look for that, which has got plutonium in it. Don't tell anybody they're putting plutonium in spacecraft that could crash during the boost stage of the rocket, because the environmentalists would get all upset. Okay, but NASA doesn't advertise that anymore. But anyway, so there are applications of welding all kinds of structural materials. Fusion welding is something where I basically start out with flames, go through arcs, lasers, and electron beams, and talk about the process. And you go from 1,000 watts per square centimeter as a heat source up to 1,000,000 watts per square centimeter, and what are the different physical interactions that occur. So if someone wanted to take fusion welding, that's a 12-unit module. You basically have to get 3 full modules of 12 units. We will be teaching 1.5 modules this semester live, and you're going to have to pick up some other modules on your own. Those of you who have taken the class before know that. Manufacturing and use of structural materials. Dr. Belmar did that. It does focus on structural materials. You don't want to say anything more about the details of what you covered? How do we manufacture?
I think the title may be a little misleading. It was material selection going through the different alloy
Classes.
Yeah, from just a general standpoint, how it's made and how it's influencing the properties.
Right.
It's complementary to your material selection that you did last fall.
Yeah, my material selection is sort of a 100,000-foot view of how do you select materials and get into economics and externalities. And Dr. Belmar's is basically looking at, okay, what type of properties can I get out of aluminum alloys or titanium alloys or steels, and how can I use those in design, okay? Solid state welding is the first part of this, my total welding course. It's 12 units on adhesive bonding and brazing and soldering and diffusion bonding, anything that's not melting metal to make a fusion weld. All those other welding processes, explosive welding, cold welding and stuff go in here. Codes and standards, that's on there twice because that was a new course that talks about if I'm going out to manufacture something, I can't just go do anything I want. There are lots of rules and regulations out there in the world, okay? And the government tells me that if I do this, some things by force of law, if I don't do it the way the city of New York says or the federal government says and the Department of Transportation, I can't sell the product, okay? By the same token, some standards contain the historical knowledge of how to do things right and not have a big screw up. So historically, some of our codes and standards have been written to correct for major mistakes. For example, the Northridge earthquake in Southern California 20 years ago or whatever, a lot of buildings and bridges came tumbling down, or they were damaged to the tune of like $15 billion worth of damage to these buildings. And a lot of the building codes were modified to allow for earthquake vibrations. Now the Japanese have been doing that for 20 years because they have a lot more earthquakes than we do. But back in the 50s and 60s, we didn't design bridges and buildings in Southern California to accommodate those things. You still read in the news about how they had an earthquake in Chile and, or Iran, and 10,000 people died because the concrete buildings just collapsed on people, okay? We actually can design things because of different codes and standards. And I talk about kind of the politics of how codes and standards fit into both regulation of the government and in engineering, and how it can be the corporate knowledge that teaches us how from the mistakes of the past, but it also can stifle innovation, okay? Deformation processing, if you're interested in forging or sheet metal forming or wire drawing or any way to form ductile materials, then that course goes through the physics of forming and processing using stamping presses and forging machines and wire drawers and things like that. Structural life assessment, Dr. Belmar taught a module on that. You want to talk a little bit about that?
We did cover fracture mechanics to some extent.
Yeah.
But if anybody is interested in more or less of a mechanical performance, so this semester we're teaching fracture class in so it's very specific to mechanical properties. It's not, this class is a lot more general. There's a lot of term of engineering. The other one is more specific with respect to how to deal with cracks.
Right.
In airframes and structure.
Yeah, it's basically fatigue and fracture, but from the point of view of a designer of what you have to consider, as opposed to getting deep into the physics of the fracture. Okay, there is this other course on fracture that the department that Dr. Belmar teaches part of on the physics of the fracture. There's a casting course here, and I called it Intro to Materials Processing because this is where I take my shot at nanomaterials. Okay, it's only about a lecture and a half about how nanomaterials will never be used for structural materials. They may be interesting for functional materials, but nanomaterials are just going to be too expensive for most structural materials unless you're talking about spacecraft or something like that. If you're building a bridge across the Charles River, you're not going to make it out of nanomaterials in spite of what all the researchers around tell you. Okay, haven't had that discussion with the department head since last Thursday. Okay, where we had a faculty meeting off-site, and I made some comment about nanomaterials, and he started telling me how wonderful they were. I thought, okay, so we have a difference of opinion. Solid state welding is the old version 3 years before. I kind of try to renew these every 3 years. So there's the old version of that. Material selection, fracture, NDT, and welding metallurgy. You're getting the welding metallurgy. This is where I had 3 or 4 lectures. NDE, I may teach a course on that this summer to the Navy guys. I used to teach some fracture mechanics, but that's sort of been supplanted. So this was years ago. Material selection has been supplanted by one that's not on here, which is the one I did last fall on Introduction to Material Selection, and this is the 100,000 foot view. Fusion welding is the old version of this one up here. This solid state welding, I've been videotaping these for over 20 years now, and how an old one got in here, I don't know, but anyway, it's on there. And then there are some other archived ones that are just a selection of some of these from even older times. Some of you, like Christine, what modules did you take last time? Okay, so you can tell people about what that is. Okay, you also took my intro, my live course, and you probably took Dr. Belmar's course. Okay, so you took 24 units live and 12 units by video. Okay, Jonathan, what did you take last time? Okay, as well as the 24 units of live stuff. And anyway, you're welcome to take whatever you want, but you can't take something you took last time. Okay, that sort of makes sense, right? So anybody have any questions on that? You have to take approximately 36 lectures, because that's what you get in a 12-unit course at MIT. Now, some of you know that I schedule this quite a bit differently than the regular MIT course. We meet every day of the week. That's a scheduled class day, 9 to 10 in this room. And if everything goes perfectly, we would be finished by the end of February with the lectures. Okay, how about that? And then we actually probably won't finish until early March, because I've got to be out of town on Friday. I think Dr. Belmar's lecturing on Friday. But anyway, I'm lecturing today and tomorrow. Dr. Belmar, I'm lecturing on the 10th. I'll give you the schedule a little bit more detail tomorrow when we know it a little bit better. Mike Baumforth is doing the 12th and 13th of next week. I'm doing the 14th. Come here for Valentine's Day. Whatever. So we do the lectures. It's front-loaded. You get things to read. You don't have to read them, but you can read them. If you read the course evaluations from prior years, One student says you can get a lot or a little out of the course depending on how much you want to do outside of class. What are you required to do out of class? What's the assignment? If you really want to do a term paper, and it would be a 10-page term paper, you can. Okay? If you don't want to do a term paper, the preferred method, most students do a presentation in class, and this will probably come right after spring break, beginning of April. We'll schedule it, and we'll do 2 or 3 lectures of your presentations a day. Those of you who did it last term, you get to come up with another topic. You can't give the same presentation you gave last term. Okay? Or if you really couldn't do either one of these, you can talk to me. I do have an old homework set on the old welding stuff of 10 problems, and you could do the 10 problems. You only have to do one of these. Okay? In fact, those of you that have been in this class before know that I give a little lecture at the beginning of how I have a bad attitude about the way we do education, that students both in high schools and in colleges are just prepped to take quizzes. And I don't think that's a very good learning environment. I started realizing this 20-some years ago. One of my kids left their high school math book on the kitchen table, and I was sitting there eating breakfast, kind of flipping through. It had 2 pages on every mathematical topic you can think of: matrices, exponentials, logarithms, differentials, integration. So everything in math could be taught in 2 pages by definition in this high school book. And all it was is I look at it and say, well, this is just coaching you to answer some of the questions on the SAT exam, right? Okay? And in fact, that's to a certain extent what happens at MIT. What do we get at MIT? We get some of the brightest students in the world who have proven that you know how to take quizzes. Okay? You couldn't have gotten here if you didn't know how to take quizzes. And so what you like to do, many MIT students like to compete with their peers by showing that they can get good grades on a quiz. You take my course and you're out of luck. Okay? There's no quizzes. There's no final exams. You can't show how much smarter than you are than your classmates. But hopefully you can just enjoy learning. So actually, you don't have to take a copy of this if you were in the class last term, but I hand out this article I wrote for the faculty newsletter on education at MIT. It's the same one I handed out. I handed out in all my classes to kind of tell you about my good or bad attitude about education and how it goes. I was very pleased for years that no one had to take my course. It wasn't required for anyone, and if you want to take the course, we're here to try to learn about different things, and maybe I'll talk about some of those things in a little bit. So that's the assignment I'm supposed to tell you. Therefore, there is no possibility of cheating in this class. So I don't have to tell you about cheating, right? You shouldn't cheat, okay? But I don't know how you would cheat in a class like this. Okay, you're gonna download some presentation off the internet and try to give it. Okay, well, anyway, I don't care. Okay, I mean, you're the one who's paying big tuition to try to get around the system. So I think that's all that I had. Sign up, schedule, assignments, and the different modules. Anybody have any questions on overviews? Yeah, yes. Yep. You have to have them done before I have to turn the grades in May. Yeah, you can start watching them now. You can start watching them on May 10th and cram them in at the end. That's another one of my philosophies. Students will come to me and say, "What do I have to do?" Give me a deadline. I mean, I'm not saying you, but I've had my own doctoral students have to write up the thesis, and one of them said, "Well, give me a deadline." I said, "No. He says, well, I work better under deadlines. I said, fine, set one for yourself. My job is to train students on how to be professionals, and a professional does not need someone else to give them a deadline. So you're a professional here. You get a schedule when you do these things. One student on an evaluation said that they watched them while they were fixing dinner at home. Okay? So in the background, they got me. I mean, I put on a Celtics game while I'm working at home, right? Fine, it's in the background. If there's a play, there's always going to be a replay, and I can look up. Okay, so if you're fixing dinner and all of a sudden you hear a story you want to hear, you can let the carrots burn while you listen to my story. Okay, I don't care when you do it. Okay, in fact, one of the problems, if I get involved in MITx or EDX and stuff, I'm probably going to have some way to ensure that the students actually watch the videos. Those of you that took the thing last term will know I don't even check up on you, okay? I do expect if you're going to, well, let me back up. If you didn't want to listen to the live lectures, you could take 36 lectures all by video. And that's one of the, to me, the beauties of this. If we videotape the lectures, anybody in the world can take this course, but only you can get credit because you paid the tuition, right? But I've been putting my course online for 15 years now, before MITx and EDX. And I know that there are professors at other universities, when they have to go out of town, they pull off one of my lectures and show it to the students while they're gone. Okay? Because it's just Tom Eagar and stories, right? And so it's kind of like having a guest lecturer, right? And someone tells the story. Okay? So if you're here, from my point of view, you're here to learn. And one of the things I'm trying to do is help you draw analogies. There are some people who just spend all their time lecturing, okay, and telling you. It's kind of like Moses coming down from the mountain and giving you the 10 Commandments. So this is the 10 Commandments of engineering, and you should learn this, right? Well, I believe in kind of a different philosophy. I would much rather convince you that you already know the answer to many things. You just never had someone tell you how to put it together. Okay, so when I'm talking fusion welding and I have to talk about arcs, one of my favorite lectures is what I call the fluorescent light lecture, where I tell you the difference between a high pressure arc, which is a welding arc at 1 atmosphere pressure, and that's what the physicists call it. 1 atmosphere is high pressure to a physicist, okay? Or a fluorescent light, which you know is at a lower pressure. You ever broken a fluorescent light and it implodes and you hear it go pop, right? It implodes because it's like, I don't know, 1/5 of an atmosphere. And it's a glow discharge, and we have fluorescent lights in this room. But fluorescent lights are cooler, right, than an incandescent light. But LEDs are even cooler. And what's the physics of giving off light? And what does that have to do with welding? Zippo, okay? Unless you're using light to weld, and some people do. They use very intense light sources as a heat source to weld plastics and things. Some people have even welded some metals using very intense light sources. But nonetheless, you need to understand the basic physics of how plasmas cause heating or non-heating, and it turns out a fluorescent light is a 2-temperature plasma. The electrons have a temperature of 100,000 degrees, and the ions have a temperature of 100 degrees C. Okay? That's why you can put your hand on a fluorescent light, because the ions, what you feel is the ion temperature. You can't feel the electron temperature, but you can see it. It's the electrons that give you light. Same thing in an LED. It's the changing of the direction of the electrons that causes them to radiate and give off light. In that case, you don't even have to heat up ions, so LEDs are more energy efficient than fluorescent lights. So what I'd get to do by teaching you welding is teach you about all kinds of little physical things that I've learned over the years. And you actually learned most of this in freshman physics, but no one ever told you how it fit together, because who was teaching you? A physicist. They haven't a clue of how it fits together. Okay? And in fact, I was a student here. And I look back and think, how come they never told me about these things? You know, I learned in thermodynamics, I learned how to calculate a heat engine up one side and down the other, but I couldn't tell you how an air conditioner worked. Did you know an air conditioner is a heat engine? No one ever told me that. I had to learn that in the gutter of going out in the real world. Okay? But an air conditioner is a heat engine. So one of the things I'm trying to help you do is learn that all these things you learned when you got the MIT science education is actually a useful piece of knowledge if someone actually shows you how to use it. Okay? And if you learn how to use it in a few examples, I bet you can figure out how to use it in other examples and be creative in your own way. Okay? So it's a different philosophy than Moses coming down from the mountain saying, here are the 10 commandments of welding. Okay? It's more, well, did you know that fluorescent lights are just a different type of arc? Okay? Or my adhesive bonding lecture in solid state welding, someone asked me to give you some examples. I call it the Scotch tape lecture. Okay? Why does Scotch tape, if you put it on the wall, why does it later fall off if it's holding something on the wall? Whereas duct tape holds things much better and much longer. But if you put Scotch tape on and it falls off the wall, why do you go over and then push it on even harder, hoping that it will stick longer? Well, it just turns out to be a viscous flow equation. Okay? And if you learn about the viscous flow equation, you'll understand why duct tape works better than Scotch tape, and dirty Scotch tape doesn't work as well and doesn't last as long, and things. Okay? And you also learn about all kinds of adhesives, right? Okay? Jordan's learning about adhesives. She's doing a bachelor's thesis on adhesives. Okay? So she's actually watched that lecture, right? And these equations have been around for years. It's just no one ever teaches them to you in context. So I kind of consider these context subjects. Any other questions? Simone, do you want to give an example of some of yours?
Yeah, I'll give a few examples.
Okay.
You can jump in too.
I will.
You know a lot.
You know me. Oh yeah.
There's a survey I remember I got on my desk last semester about feedback from graduate students and undergraduate students, and one of them was they wanted more contact with faculty. Well, look at Professor Eagar right here. He is always available. When I took his class back 10 years ago, right about, I was doing some research and I was trying to do electroless nickel on a small nano wire to be able to run an experiment, and I just went to him and he knew all about it, a lot more than everybody else I talked to before talking to him. It happened in the project sometimes. If you work for a company before, or if you have something in your thesis that you're trying to develop, there's nothing wrong with making that your project. You just have to frame it slightly differently, and we are really available to help you. You know, you worked on any design project or something that you had a prototype that was not working. All I can tell you is we deal with those things a lot, and we're happy to provide free advices. It comes with the class, and for me it's easier if you tell me ahead so we can meet after class or set up a time. And probably the same with Professor Eagar. He has an assistant that can take you in the calendar to meet with him. The examples. Well, first of all, this is slightly revised, so it does have the fall classes here. It's the same layout that's online in terms of what has been videotaped, except that it has the fall, and I've specified, so I've given material selection in 12 hours as well, but everything else that's on me here is 6 hours. So I tend to be a little bit more to what is needed as the basics in those lectures, especially the one last fall on environmental and mechanical behavior. I talked about corrosion, which a lot of students in the class really liked because it's not something that's taught so much. It's not cool to talk about corrosion, even though it is very important to practicing engineers. And that's an extension of what Professor Eagar was saying about nanomaterials and what
is taught in class in terms of going to the thermodynamic equation as opposed to how you actually get something done in terms of engineering. And we are trying to bridge that gap a little bit. A lot of it comes from experience. I have to say the first 6 months I worked for a large consulting company, I wasn't very helpful. By the time I had to turn in the assignment, I had spent so much time just learning a lot of practical stuff. And it's not that there's anything wrong with this. I mean, I went through the process like you guys. I did a lot of research. I had a lot of basic skills. I had to learn how to apply it to, it was still a very broad consulting structural engineering area. But it probably took me a few years before I was really able to answer questions without having to do a bunch of research on the first place. And we won't be able to take you away from that, but I take that to the extent that some of Professor Eagar's examples and stories help you realize that there's things we know, things we don't know. There's nothing to be shy about not knowing. The best way to learn is for someone to teach you, or to spend the time and realize that you need to, get more knowledge, get more data before making a decision on a prototype or anything that you're building. So in terms of work, and that was what I was going to do for overview today, if you are a practicing engineer, so if you're not in a research laboratory, a lot of times you end up having to be involved with a lot of phases of a certain project. Sometimes you, at the very beginning, you have to decide which material we're going to use. You should be thinking about how we're going to put it together. I can't tell you in recent years how many times in the class I had a student come up and say, oh, I'm going to build a pressure vessel out of spring steel. Okay. Now, is your pressure vessel going to be a sphere that somehow you manufacture without any joint? And if that's not the case, you need to think about joining. So, it may look very simple and boring, but there's nothing more important than to think ahead. If you say I'm going to do a cylinder, first of all, you need to think about these corners. They're going to try to flatten out and open. So if you put welds right there, there's going to be a lot of forces, especially if it's welded from the outside on the root of that weld. So a lot of times you want to make this half a sphere. And that way you get away from trying to open up that weld. And maybe you put a lap joint, like these propane tanks that you can buy at Home Depot. But you need to think about it. And if you're thinking about using a spring steel, it limits you, because if you're going to do the fusion welding, you'll learn in the metallurgy class, you're going to have a lot of problem with your strength. No matter what, you'll lose. You can either lose the ductility, you can lose the strength, you will lose both probably most of the time. So you try to put these joints away. And, again, it's just feedback from the class. And you are all smart people, but this came 2 or 3 times over the last year. Just not thinking about all of the material selection process. Just thinking about trying to optimize. Oh, well, I'm going to reduce the strain. I'm going to use aluminum. And you will learn through the welding metallurgy that there are issues in terms of welding aluminum as well. It's not that there are no easy way around it, but in terms of just being an engineer, selection of material goes with joining. And you're lucky this semester there's going to be a lot of joining discussion. Now, I wanted to frame today's overview in terms of this design, failure analysis, and rehabilitation. For design, I picked this project that I worked on most of last year. Different variation, this is a medical device that you do an open heart surgery, and then you form it to a certain shape to put it in contact against the heart on the outside, and then you have a cooling gas that is fed through the inner carrier here, and you have 3. The inner carrier gets split in 3, so you have 3 points here where that gas comes out. It's a liquid and it expands. That creates cooling. So going from essentially an expansion You have a lot of pressure on the inside, no pressure on the outside. So there's a return here that is low pressure, and there's a supply that's high pressure. So when you turn on the pressure and you cool it down, it will essentially create ablation on the heart, and then you cool it back up, and then you can move it away. This happened to be a device that is sold, and they have a good fraction of the market. The client that contacted us to work on this, they did want to improve the flexibility, because this is the section that goes, it's a part of the section that goes on top, and what the surgeon wants to do is he doesn't want to use tools. He wants to be able to do it with his hands. So the risk of forming a kink, and I won't do it on this one. I had plenty of tube, and I'll pass it around, but please don't make too many kinks in it. I have tubes if you wanna go through the formation of kinks. There's a lot of, in that simple device, there is joining. If you look at the manifold over there, there's some barbs to connect. You can see they have a little teeth pattern. The barbs look like this. That's to put a tubing on top. You have to be careful on how you design these if you don't want leaks. There are a lot of different design parameters. This specific connection where the manifold is not in the body, but at the same time, if you're going to go through the process of making your own device like this, any leak, whether it's critical or not, is critical to your reputation. If you connect everything together and then there's some nitrogen gas that starts to come in the operational room, you're in trouble. So when we talk about safety factors, if you can afford it, just make it stronger than it needs to be. It's going to be at low cost for such a small device. When you're in the working zone, so what really goes in the body that you have to bend, if you make it too big, it's too hard to bend. If you, again, make the wall thickness too thin,